Hi, your 11s, this is Mr. Lim here again, and this is our video on thin layer chromatography, one of our first chromatographies that we're going to learn about. Right, so we're going to work out what thin layer chromatography is, get some definitions, work out how it's actually used in analytical techniques. Okay, so all right, so what is thin layer chromatography? Thin layer chromatography is a thin layer of substance, is used as the stationary phase. Okay, then the components of the mixture are then dissolved into a mobile phase, and then the mobile phase and the components move up through the stationary phase, up being the main word here, via capillary action. So what is capillary action? Capillary action is the movement of a liquid through a thin substance as the attraction between the liquid and the thin layer allows the movement of a small amount of liquid up the thin layer. All right, so what the hell does that mean? So you've got here two glass tubes inside some water, right? What happens is that a meniscus is formed. That's that curved line here. And that curved line is formed because there's attraction between the water particles and the glass wall, right? So because there's attraction between those, they move upwards and kind of cling onto the glass wall and create that meniscus that you can use to, measure liquids and stuff like that. All right. The idea is that when this tube gets smaller, more of those water particles can kind of climb up on top of each other and climb up on top of each other. And then if you get it skinny enough, this continues to move up, 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 or I guess upwards this way. So upwards this way, upwards this way, upwards this way, and they continue to rise up, right, all the way up this tube, okay? Which is why it has to be thin layer chromatography, because without this thin layer, the capillary action doesn't work, right? So it's effectively, you don't need to know much about it, but the idea is that the water is kind of clinging to the sides or clinging to the thin layer and moving up the system. All right, so it's thin layer chromatography. Okay, so the components dissolved within the mobile phase will move up with the mobile phase through the stationary phase and stick to the stationary phases differing amounts depending on the polarity, which we covered in the last video. Okay, so two common thin layer chromatographies are, you've got your paper chromatography and your thin layer, also is a silica gel. Okay, so the paper is made up of, paper, and the paper itself is made up of cellulose, which is the stationary phase. Okay, the thin layer is made up of a silica gel. Right, and these are both very polar substances. Okay, very polar substances, and so when you use water to bring components up through these thin layers, the cellulose and the silica gel, or the silica gel, act as very, very polar substances, and therefore polar substances will stick to those stationary phases varying amounts, and therefore if it's a polar component, it will move slowly through these thin layer gels, right? But ultimately you need to read the question and find out what type of polarity these things have, right? But generally paper chromatography and thin layer chromatography, they have very polar stationary phases. All right, let's move on. Okay, so what happens is that the components, as they move through, they can only move as fast as the mobile phase. Okay, so the mobile phase is what they're dissolved in. The mobile phase will be dragging them through, and generally the mobile phase will move faster through the thin layer compared to the components. And so therefore there will be a solvent front. What is the solvent front? It's the furthest the mobile phase has traveled in a period of time. Okay, so what's happened here on this side here is that this is a piece of paper or a thin layer of silica gel, right? They put a sample as a dot there. So if it's paper chromatography, you might put your marker pen or your marker dot there, okay? And then they've dipped this end into water, okay? And so the water has moved up through capillary action. As it's passed the sample, it has dissolved the sample and turned it into, dissolved into that water. And then it's moved with the solvent up varying amounts, that's these components, but the water itself has moved this far. So, well, I don't know, this diagram here is not very labeled very well, but the solvent front is that level there, right? How far the solvent has traveled in a given particular period of time, right? So that's the solvent front, okay? Where the mixture of components starts is the origin. So the origin would be here, okay, this black dot here, right? So you've got the solvent front and the origin. And then the idea is that each component will move a different amount on the thin layer depending on the polarity of the components and the stationary phase. So that's what we've been dealing with in the last couple of videos. All right, so let's move on. So for a given set of conditions, right, components in a mixture will always travel the same proportion of distance traveled by the solvent front. Okay, so proportion meaning like, oh, it'll move 60% of how far the solvent front has moved, or 40% of how far the solvent front has moved. Okay, this proportion traveled is known as the retention factor. Okay, so the retention factor can be calculated by the distance the component has traveled compared to the distance that the solvent front has traveled from the origin. Okay, so the distance that the solvent front has traveled from the origin in this one is this far here. Right, the distance that the components have traveled, well, the red one has traveled this far, the green one has traveled this far, and the yellow one has traveled only this far. Okay, so as a proportion, right, you would take the distance traveled. So let's just say for the green one, we would measure that distance, and then we would measure this distance, and we would take this distance divided by this distance, and you would get a value. Okay, and that would be its retention factor. And if you haven't worked it out, since the solvent front is always going to go further, the retention factor of these things is always going to be less than 1. All right. So let's go have a look at how to calculate some of these here. Right. So the RF for this particular component is how far the component has traveled from the origin. So if here's the origin, here is the component. So how far has it traveled? 2.1. Over how far the solvent front has traveled from the origin. So that's the origin to the solvent front. So that's 2.8, which happens to be some value. What value is that? 2.1 divided by 2.8 is 0.75. Okay, there's no unit on this, it's just the ratio. Okay, so retention factor of 0.75 for that particular component. All right, this one over here, the RF is equal to, what is it going to be? 4 divided by 5.5, which just happens to be some value. Right, 0.73. Okay, again, no unit here. All right, so that's how you would calculate retention factor. And what you've also got to be able to do is work out how to rearrange this equation so that you can work out how far components will travel depending on the solvent front. Okay, so say that, for example, this value here wasn't 5.5. Let's say that value here was 7.5. What would this value over here be? Okay, so we know that the RF is going to be 0.73. So we would say, okay, then 0.73 is equal to the RF. We don't know how far the component has traveled, but we know that the solvent front traveled 7.5. So we would rearrange that equation as 7.5 times 0.73, which will be equal to something, 7.5, 5.45 centimeters. This will have a unit because it is how far it's traveled. All right, so you can rearrange those equations to work out how far components have traveled or how far solvent fronts have traveled as well. Okay, so here's another one here. Say your component actually travels a variable amount. Okay, so there's this kind of a smear on where it is. Generally, what you would do is you would take the value from the center of that smear, and then you work it out from there. Okay, so you will sometimes be given a scale rather than just told what it is. So you have to actually use the measurements there. So the blue one is approximately what? That's 6 centimeters. 6 centimeters. All right, over the 6.5 centimeters of the the solvent front. Okay, so the RF of the blue is therefore equal to 6 over 6.5, which is some value, 6 over 6.5, 0.92. Okay, the RF of the pink would be equal to, so we would say that that is maybe 4.8-ish, 4.8 over 6.5, which happens to be 4.8 divided by 6.5, 0.74. Okay, and the RF of the yellow would be equal to, let's just say that's 2.55 over 6.5. All right, 2.55 divided by 6.5 is equal to 0.39. Okay, so if you have a smear and it's a range of distances, you don't go by how far it's gone to the tip, you go by the center part. Okay, then here we go, next. The fact that under certain sets of conditions, components will always travel the same proportion of the distance traveled by the solvent front allows TLC to be an analytical technique for a qualitative analysis of mixtures. Okay, qualitative being like I identify what's in there. So if a known substances are run under certain conditions, so first of all, you run your knowns first, then you run your unknowns under identical conditions, then you work out their RFs of your unknowns, and you work out your RF of your knowns, and if they match, then you can identify what that substance is. All right. However, you must have these run under identical conditions, otherwise RF values will be different. Okay, so you must run it under identical conditions, and you must run your knowns first before you run your unknowns, otherwise you're kind of comparing unknowns against nothing. All right, so for example, here's a chromatogram with a whole bunch of different things. You've got a band compound here, which is this dot over here, right? And you've got a couple of unknowns over here, right? And you've got information about known chromophores, which are these components, and their RF values over here. Okay, so let's have a look at some of the questions and how we might answer them. Okay, so what is the band substance? Okay, so the band substance is here, so we would have to use the scale over here. And so this is approximately, goes to like, I don't know, this line over here. Right, so that is 4.8 over 7, which happens to be some value. 4.8 divided by 7, which happens to be 0.69. Okay, so therefore the band substance is chromophore 3. Okay, because we can see that 0.69, 0.69, that's chromophore 3, so that is our band substance. Okay, which of the dyes contain the band substance? Now we can look at all of the dyes and then look for something that has a RF of 0.69, right? Alternatively, because this is actually run on the exact same thing, you can just say, well, anything with the same RF value is going to have that band component, which means if it's moved the same distance, then it's going to have that band component, right? So which dye? Dye C contains the band component, right? Identify the dye that is each of the chromophores is present in. Okay, so we know that chromophore 3 is the band substance, and we know that one's in dye C. Okay, let's have a look at the rest. So we would take this RF value. RF is equal to component over solvent front, and we would say, okay, then 0.29 over 7. 0.29 equals something over 7, how far the component has traveled. Okay, so therefore the component has traveled 7 times 0.29, which is equal to something. So 7 times 0.29, 0.7 times 0.29, which happens to be 2.03 or approximately 2. So then you would say, okay, well, here's 2. Which one has traveled approximately 2? So that one's there. So that one's also C. Okay, C has that chromophore as well. Okay, then we would look at the next one. So we would say, okay, then this now is 0.2. Oops, 0.2. And so this would change that calculation. The solvent front stays the same, but this is now 0.20, which is equal to 7 times 0.2, 1.4. So then we would say, okay, 1.4 happens to be around about here. Okay. So 1.4 might actually not be D, but it will be A. Let's just say that it's A. Okay. So that was 1.4. So that'll be A. Right. We can do the same for the next one, 0.77. Right. So 0.77 is equal to this one over here, 0.77, which gets you the value, 7 times 0.77, 5.39 or 5.4. Okay, so 5.4 is over here, and so that might be in D and in A. Okay, so that's D and A have chromophore 4, right? And then lastly, the 0.39. Okay, 0.39, put it over here as well, and that will be 7 times 0.39, which will be equal to 2.73. And where's 2.73? Or 2.7-ish. So 2.7-ish is over here, right? So 2.7-ish is over here, so that's B. Okay, so using the RF values, you can work out what things are as well, given the RF values and information from those chromatograms. Okay. Finally, the idea is that TLC only works if the solvent front does not reach the end of the chromatogram. So the chromatogram is the actual piece of thin layer, right? And so your solvent front can't reach the end here, because if your solvent front reaches the end, right, the solvent front can no longer move forward or up any further, but the components will continue to travel. Okay, so what happens is that the water reaches the end here, right, and then the solvent front can no longer move upwards anymore. But these components here will still continue to move upwards, right? And if they continue to move upwards, and we're comparing the solvent front versus the how far the components have moved, therefore the solvent front value becomes inaccurate, because your solvent front can't move any further, and it would be higher if it was allowed to move. All right, so the solvent front value becomes inaccurate, and therefore you can't solve anything with RFs. If you do leave this TLC running for too long, what happens is that all the components will all recombine at the end of the chromatogram, because if you think, at some point here, this red one will reach the end and then stop, right? Then the green one will reach the end and stop, and then the yellow one will reach the end and stop as well, and then they'll all recombine at the end. Okay, so make sure that your thin layer chromatograms don't allow the solvent front to reach the end, otherwise they become useless. And that's it. Adios.